My life, I believe, yes. Hey everyone, I am Ashish. Welcome to the AI Bootcamp. So, in this video, we're gonna talk about deep learning. We're gonna execute some ANN with mnist dataset. And if you don't know mnist dataset, then I will take you to Google and we'll have you look at this dataset called mnist. I don't know the full form, Modified National Institute of Standards and Technology, but it's a dataset of 70,000 images with 60,000 in the training set and 10,000 in the testing set. And the images are grayscale 28 by 28 pixel. Let me show you how the entire data set looks like. So this is how it would look like. So handwritten digit data set it is. And we will be training a model to classify basically if a user gives a handwritten digit, the machine should be able to classify okay which kind of digit it is. So digit recognizer will be building, but do expect it to make some errors because that data itself contains some errors. Like take a look over here. Like there are a lot of digits over here. Let me select this one. Yeah, let's take a look over here. All the twos looks like two, but this one, this two, I hope is clear to you. This two doesn't even look like a two. And this is looking like one. So even the data set is not, I would say, 100% optimum. So you cannot expect the accuracy to be 100% either. And let's take a look at this 7. Looks more like a, no, it looks like a 7 only. This one is a weird 8. And what else? This one looks like a 9, give or take. Chalo. Anyway, uh, let's move on to deep learning. So what deep learning is in a nutshell is advanced machine learning. So what we have discussed so far is not theory, no theory at all. Our agenda is not to discuss theory even in deep learning. Our agenda would be to make AI systems using deep learning without even having to understand the mathematical theory behind it. But there will be times where you need some intuitions. So let me give you the TensorFlow API. So TensorFlow dot Keras. So we will be using Keras with TensorFlow. So these guys just say you can install Keras from blah 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 blah. It's not that easy to install it, but we have done the installations for you. So very well. Anyway, API guides. So there's this model API, how to use the model class. The entire API, the entire documentation is very well read. Let's go into the lab section. So I'm going to launch the labs, select the Docker container, and open code server. That's it. The entire GPU labs is ready. And because we are right now in the deep learning phases, we will be using the GPU virtual environments rather than the CPU virtual environments. Because in when you talk about deep learning, you need your systems to be on GPU because GPU has parallel processing. You can assume that if your CPU is taking 10 seconds to run something, then your GPU would take maybe zero point 0.1 second. So it's like 100 or 1000 times faster than a CPU. GPU is very much faster when it comes to deep learning. So anyway, import statements, I have some, we have selected the TensorFlow kernel. So opt env tf bin python. So this is the TensorFlow kernel. And if you don't know how to select this kernel, just go to my GitHub and open this 14-day bootcamp and read this README file. So over here now, I've listed out like there are four environments here, over here. TensorFlow environment, PyTorch environment, data science environment, and one ATS resume environment that I'm just using right now to to make some projects. I don't know if this environment will be in the future or not, but I can always create more as the need requires. So how to activate a Python environment? You just go source opt env tf bin activate. This will activate the tf. PyTorch source opt env torch bin activate. This will activate the PyTorch environment. And why do I keep separate environments for TensorFlow and PyTorch and data sciences? Because there are conflicting packages. So the PyTorch has a different CUDA requirement. CUDA is for installation of GPUs. GPU is what we will be running our deep learning models on. So TensorFlow has its own CUDA versions. Uh, PyTorch has its own requirement for CUDA versions. And basically, your data science environment would have its own, requirement for a NumPy module. NumPy, uh, I believe we have introduced NumPy to you, import NumPy as NP. So in all these three environments, you would see that NumPy version would be different. And as for this thing, ATS resume, you can activate it using this command source optenv ATS bin activate. With that said, let's go back to the labs. Where are the labs? Oh, right here. So import TensorFlow STF, NumPy, Pandas, Matplotlib, and Cvon. I have imported. Then this is how we load the dataset. I just find this over at Google. So over at Google and the Keras API, tf.keras.datasets is a module using which you can access the mnist dataset. So it by default gives you this kind of structure where it gives you two tuples of xtrain ytrain and xtest ytest. So if you print out the shape of xtrain ytrain xtest and ytest, it will give you 60,000 images of 28 by 28 pixels. So imagine in this way that we have one image of 28 row pixels, 28 column pixels. We will discuss more about what these pixels are in the OpenCV section, in the image manipulation section, where like in the additional tutorials, we will be discussing everything like what is an image and basically what are color channels and so on. I'm just giving you an overview of what we will be discussing later on in the sixth module of additional tutorial. So like this is a 2D image. So this is also a 2D image of 5 rows and 3 columns. So basically we'll discuss it later on. So anyway, you can inspect the data types of these things. It will be numpy.nd array, which we are very much comfortable with at this moment. We are not, I never said that it is a nd array that we are working with. We don't need to know like what sort of array we are working with. Now let numpy handle it, right? Our job is to create systems, not to go into the nitty gritty of what's numpy, what's nd array, what's this, what's that. So upon visualizing one image, by the way, take a look. I'm using plt.imshow for image show to visualize the entire image of extreme index 0, the first row, and it's 28 by 28, 28 rows, 28 columns. So there you go. This is the level 5. You want to display multiple plots, then basically you can. It's a hidden trial, the API. So there are a lot of ways to run this API as well. So I'm using for I in range 10, for I in the range of 10, plt.subplot, meaning create a subplot for me with 2 rows and 5 columns, I believe. Yeah, 2 rows and 5 columns. So 2 rows I have and 5 columns I have. And I plus 1 meaning that the first plot is the 1, 2, 3, 4, and so on. It's going till 10. All right. Pixel value distribution, you can check. 0 to 255 is the 0 being the lightest pixel, darkest pixel, and 255 being the brightest pixel. And our data set is very much balanced. All of these categories of handwritten digits are almost equally distributed. No worries over there. So remember that sometimes we need scaling for our algorithms to work faster. Remember, I was talking about this in the clustering section. that maybe one column feature column is in the range of thousands and another feature column is in the range of, let's say, 1 to 10 only. So sometimes you need to feature scale them into like say -3 to +3, or 0 to 1, or compress them into a range of -1 to 1. Why? Because I don't want my model to learn that higher the numerical value, higher the importance it has, right? I don't want to create any bias like that. So for that, I'm saying let's normalize this entire thing by dividing by just 255 only. All right. So max value after normalization is 1, because max value before normalization is 255. So if I divide entire thing by 255, the range is compressed from 0 to 255 to 0 to 1, right? All right. And your matplotlib knows what a normalized image looks like. So if you give it the integers of 0 to 255, it will plot the same thing. If you give it the normalized image of 0 to 1, then it will plot the same thing. So normalized image and this one and the not so normalized normal image, both are printed in the same way. So all right. So at this point onwards, I would like to, take the notebook of a Python script, but just to make you understand, I'm using notebook just to make you understand, but actual workflow we will do in the Python notebook. We can do this over here as well, but it's a better practice to choose Python notebooks to do the entire thing. Because what happens is we train a model, we create some plots, we save the model and the plots, and then we load the model and load the model and make a system out of it. So you need a particular Python script. You need GitHub version control for several developers to work together on a single project, which Notebook does not offer. So anyway, right now let's discuss the Notebook flow only. I'm importing the TensorFlow from the very start, and what else? I'm like over here I'm normalizing. Then I'm saying reshape it into as many rows, but 784 columns. 28 by 28, if you do, it would be 784 now. Let me check. I'm not good with maths as such. 28 by 28, 784. Yep, correct. So I will say run all the cells above. It will take some time, but the TensorFlow kernel shouldn't take much. Yep, it just happened. All right. So see, when you're creating a model, let's take a look at what a model is really first. So I'm going into deep learning sections. So deep learning, ANN, artificial neural network. What does it look like? Basically, people will tell you it looks like this, where you have input layer as the data, some hidden layers, one hidden layer or two hidden layer or three or four or any kind of n number of hidden layers. Then there is the output layer, which is the prediction layer. But basically, what it is really your mathematical equations. But to simplify it, we just say that input layer has some neurons, hidden layers has some neurons, and output layer has some neurons. Just to simplify, we call it a neuron. But individually, all of these neurons are nothing but y equals mx plus c. I just don't want to get into the maths of it, but just assume that individually, all of these neurons are nothing but y equals mx plus c only. This is the data point into a flattened out shape. So I know that it doesn't make sense at this moment. So let me take the entire data set, and before training a deep learning model over it, let's just use a logistic regression and then see the output. So at this point, we have loaded the data set. All right. We have normalized the image. All right. Let's use SVM now. Have we ever used SVM for classification? I don't know. So let's use it right now live. Let's see if it throws any errors or if it's working fine. So from sklearn dot svm, import from me svc. Does it work? Yeah, it does work. Fortunately, it works. So this is my model one, or let's just call it Apple. I would call it Apple model because why not? SVC, and the kernel is RBF by default, but I'm just explicitly saying again that I want the kernel to be RBF. I'm executing the cell just to make sure that syntax is working fine because I'm not good with remembering syntaxes. So then I say apple dot fit. But see, before the dot fit, I need to give it X train and Y train. But the point is, right now my X train shape I have reshaped. I had to reshape the entire thing into 60,000 rows and 784 columns. So let me visualize it first for you. Like if I were to visualize this entire thing, it would go something like import pandas as PD, then PD dot display more columns was something like that. I want to display basically 784 columns. Now, so there's a syntax like PD dot display max rows or something like that. It was. Let's just search it over at Google. Pandas display more columns. Stack Overflow, best friend, and yeah, it's these three statements. I need to copy and just paste it over here. All right, good to go. Then I'm saying PD dot data frame and let's print out the X train. It's throwing me a value error. Must pass a 2D input. Okay, 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 okay. Have I not run this cell? Let's run this cell. C is not defined. What's C? What is exactly C? Have I? I might have done some mistakes over here. Okay. All right. So take a look. mnist dataset I have flattened out. What previously was a 28 row, 28 column pixel is now a flattened out array of this 0th row. This first row is a number. And what number it is? I don't know what number it is really, but I'm just showing you that it has some values ranging from 0 to 255. I mean, right now they are ranging from 0 to 1 only because we had normalized it now. So somewhere do you see the value of 1 or something? Yeah, right here 0.99, so it must be the brightest pixel. 6 now 79th pixel is the brightest pixel over here. So anyway, this is the data frame, at least the data frame version. Remember, and when you have the data frame, you would have to have the labels as well. So I would say something like my train. So first image is of the digit 5. First row belongs to the digit 5. All right. So I will say apple.fit for me x train comma y train. Let's run this cell just to make sure if it does not throw any kind of error. And because it's a very big data set, at least for a machine learning perspective, it's kind of a very big data set, so it's taking some time to run. I expect it to take 30 more seconds. In the meantime, talk to me. I'm bored. Not really. I'm very excited about this entire thing. Almost done we are. X train, Y train, please be done. Okay. Now it's taking longer than expected. And it's totally fine that it's taking longer than expected because in machine learning, models take a lot of time to run. Hmm. But now it's reached a limit where I'm like losing my patience. Okay, like 1 minute, 20 seconds. Till this model runs basically. Till then, what we can do is we can write the next part of the code, which is xtrain. I have written xtrain. Okay, xtest. No, I have not written xtest. Ytrain I have written. Ytrain I have written. So it should be done by now. But okay. So the next step, if you recall, is apple dot print Apple dot predict from X test, and whatever this prediction is really, you save it as ypred, remember? And when you save it as ypred, you go something like from sklearn.metrics import classification report. The model is trained over there. So print, it took around 2 minutes, kind of very slow. So print classification report, and the first are the actual values. So actual values are y test, and second are the predicted values. So let's print the classification report now and see basically what's the accuracy or precision recall and so on for the each of the classes of 0 to 9. We have 10 classes, right? If the model was trained, if the model training, the model took like 2 minutes, of course, predicting it will also take some time, but let's see how long. Basically, what I'm trying to do is before we execute any deep learning model, I just want to show you that whatever you're trying to do with a deep learning model can very well be achieved with a simplest or simpler machine learning model as well. It's just that when we are after more accuracy and less explanation, then we go after deep learning. So right now, take a look. 98% is the accuracy, and precision recall for the class 0 is 98, 99. F1 score is 99 with support of 980 examples. And overall, it looks fine to me. Let's display a confusion matrix. What do you say? Or let's not display it right now. We will display it later. So now that you have seen SVM model, let's try to run a logistic regression model. It will be faster, I promise. From sklearn dot linear model, import logistic regression. And this time I'm calling it Mango. I'm saying Mango dot fit, and you should be at this point very much comfortable with this kind of syntax that I'm writing. So I'm training the model right now, and then I will say something like y red for mango is mango dot predict. The model is trained mango dot predict on X test. Then I will say something like print classification report, and I will go y test for the actual values, y pred mango for the predicted values. And the logistic regression model also is giving me 98% accuracy. And logistic regression was very fast to train as well. Take a look. It only took 14 seconds to run, unlike SVM. And now let's go to the deep learning model. So basically, in this deep learning model, even if you forget the API, it doesn't really matter. Even if you forget the syntax, doesn't really matter. You just need to go to Keras website, something like this. There's the model class, the sequential class. Even in the sequential class, there are various ways of using the model. So let's take a look. In the sequential class, first of all, you initialize the model by saying keras.sequential. But now that TensorFlow has keras, so you would write something like tf.keras. Anyway, you go and create a sequential model. Sequential means run the layers one by one by one by one by one. So from the left to right, or you can say from the top to the bottom, run the layers one by one by one. Don't be like, if you're running the first layer, then go to the fifth layer to execute it. Don't mismatch the layers. Sequential is one of the best models to work with, at least in the beginning. So this is the syntax: model equals keras.sequential, then model dot add one layer, model dot add second layer, model dot add third layer, and so on, model dot add fourth layer. That was the one way of instantiating a Keras model. Another way is, I believe right here it would be, yeah. Another way is you just define a model, and inside like in one go you define all the layers that you want to. So keras dot sequential, tf dot keras dot sequential, and then you would say something like layers dot dense layer. Dense layer meaning all the layers which do the mathematical computation. So you don't need to know what mathematical computation they are doing. Just know that they are the brain cells of the neural network. At least in a simple lingo, you would call it the brain cells of the neural network. But don't actually assume that this is a brain cell of AI, because AI is nothing but mathematics, really. And we will break down a lot of these mathematics later on. So anyway, layer.dense, create for me a dense layer, create for me a dense layer, create for me a dense layer, and so on. So this is the API I will be using at the moment at least. So from tensorflow.keras.models, import for me sequential. Then tensorflow.keras.layers, import for me the computational metrics layers. So this is the computation math layer, which is called dense. It is also called a fully connected layer. Fully connected because if I show you the diagram, let me show you the diagram for a fully connected layer. Fully connected layer. So fully connected means that each of these neurons, let me zoom in a bit, each of the neurons, like let's say one is connected to ABCD, two is connected to ABCD, three is connected to ABCD, and so on. A is connected to all the 1 to 9. So that's a fully connected kind of structure. So that's what a dense layer is really. Connecting everything to everything. Every previous input to the subsequent output. That's what a dense layer does. So first of all, I'm saying let's create a sequential model, and as a list, pass three dense layers into it. The first layer is a layer of 128 neurons, or you can say 128 equations. Then I'm activation as I'm saying ReLU, which just means that really if you don't pass any activation, it would be simple linear regression model. So you just, if you don't know what ReLU means, it's rectified linear unit. No, actually, if I'm to make it simple, it gives the model a little bit more complexity to think. That's what ReLU is. I mean, if I am to show you ReLU, it's rectified linear unit only. So this is how ReLU looks like. But what exactly does it do in the backend? So take a look. This is the ReLU, this is the GELU. This is the first time reading something like a GELU. Oh no, I've seen it before. Anyway, this is the ReLU, this blue line. So it says just don't make anything negative. Whatever you have below zero, make it zero. Otherwise, it should be a straight line. Like if we were not using the rectified linear unit, if we were using only the linear unit, then we would be creating a straight line, just like a y equals mx plus c kind of graph. But now I'm saying rectify it so that the predictions are never negative. Like in the case of house price prediction, if you use a linear regression kind of model, predictions could be negative. But can there be ever a price with, I mean, can there be ever a house with a negative price? No, there can't be. It's like buy a house for me, I will pay you money. It's not possible. So that's why we use rectify a linear unit. In some cases, we used to use sigmoid as well, but simple thing, simple. Let's if to keep the matter simple, I'm gonna say let's use 128 equations of ReLU, activation equals ReLU, and the input shape of the data is 784 columns dot. All right. Okay. Then and in the second hidden layer, I'm taking 64 equations of again ReLU. But now the activation changes for the third layer. I'm saying how many things do I need to predict? I need to predict 10 digits. That's why I will say create a dense layer of 10 equations because I need 10 predictions, 10 predictions, one for the digit 0, one for the digit 1, and so on till digit 9, 0 to 9. There are 10 digits we have. So that's why we are in the last layer. Last layer is for the output layer for the prediction. So predictions should match the number of neurons, should match the number of things to predict that we have. And over activation side, we have softmax, which is nothing but a generalized sigmoid. And sigmoid is nothing but something that transfers your linear regression line into probabilities. Let me show you. It should be sigmoid. This is the sigmoid function. All it does really is it takes a straight line and converts that particular straight lines into probabilities ranging from 0 to 1. Like probability is going from 0 to 1, right? Well, take a look at the y-axis. It's nothing, don't be confused at what this sigma x is, what this 1 divided by 1 plus e to the power minus x is. Don't be confused with that. We don't even need it really. Researchers did their way for us. Our job is to use it. So 0 to 1, let's say if I am at this region, at this line, where it says 0.8 probability, I would say 80% probability, right? So sigmoid function, what it really does, it takes a linear line and gives it a non-linear nature. And with the non-linear nature, we have a prediction of probability prediction. And what softmax does is basically sigmoid was for only two classes, yes or no. Remember, originally when we were dealing with the churn data set, either the customer will churn or not churn. That's only two possibilities. So what we were calculating for the log probability was like what's likely the probability that a particular customer will churn. 0.8, 80% that this person will churn. So only two outcomes were there. That's why we were using sigmoid. Not really sigmoid, but we were using log equation over there. But it's okay if you don't get what the log equation is. But all right. Coming back to the topic, softmax is nothing but your generalized sigmoid function. So assume that you are using 10 sigmoids over here. Cool. All right. Then I'm saying model.compile, optimize, optimizer equals Adam. There's not Adam Eve going on. This is adaptive movement. It's just a technique of optimizer. You don't have to really understand the mathematics behind it. Just do understand that if you ever forget the optimizers, Keras gives you a lot of optimizers to start with. API models over here. I hope it is visible. Let me zoom in a bit. Models API, layers API, callback, optimizers right here it is. Stochastic gradient descent, RMS prop, adaptive movement, and I think adaptive movement will work for you 99% of the times, really. But it's really a hit and trial of what kind of optimizer will work in what kind of cases, which kind of cases. So, but if you're not sure which optimizer to use, just go with Adam, and you could always like hyperparameter tune, train the model with different optimizers. But I doubt that you would get anything better than Adam. Basically, if you don't have a very strong machine, you use SGD. If you have a good enough machine, you use Adam. That's the two only that I recommend to use, at least in the beginner stages. All right. So then the second thing is, how do you calculate loss? In loss, this is like calculate the error. How do you measure the error and minimize it? So the error is not mean square error because right now we are predicting digits. We are predicting probabilities, 10 probabilities. So we have the cross entropy error for that. Categorical cross entropy or sparse categorical cross entropy. I'm saying sparse right now because like let's say there are two types of cross entropy as well. There's a sparse categorical cross entropy, which is something like blah 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 blah. But all it really means is if you have your y label, y prediction, y test. If you have your y test in a normal numeric form, which is not one hot encoded, so these are sparse labels. That's why you say sparse categorical cross entropy. And if you ever forget this entire whole thing, don't worry, I do forget all of these things as well. All you need to do is just go to the Skeras documentation and choose losses. And in the losses, there is this sparse categorical cross entropy class. I hope it is visible at your end. And basically, you just copy and paste this entire thing. You see the copy button over here. Just copy it and paste it. Otherwise, if you don't want to copy the entire class based API, you can just use this name, sparse categorical cross entropy. But if you have one hot encoded labels, you would have to use the cross entropy, which I will also show it to you. If you had one hot encoded labels, somewhere around there, categorical cross entropy, yeah, right here is the categorical cross entropy. So categorical cross entropy right here that we have, we would have used categorical cross entropy loss if we had one hot encoded labels. That's the only difference between sparse and without sparse kind of thing. All right. Moving on, we are choosing the metrics of accuracy, but you could very well go ahead with accuracy of recall, precision, and if you like ever forget the spellings of it, the metrics, the API also gives you the metrics as well. So let's see where the metrics are. Operations API, optimizer metrics. Yeah, right here is the metrics. So base metrics, accuracy metrics, regression matrix, you have regression for numerical number prediction, classification matrices, area under curve, precision recall, blah 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 blah. There's so many metrics you can choose from. I'm just choosing accuracy at the moment because for now we have a balanced data set, so accuracy will work. So how to train a model? You just say model.fit, give it X train, give Y train. How many epochs to train? Epochs would mean something like how many times do you want your model to see the data? One time, two time, three time, four time, five time, and the more the number of epochs, the better the model gets. Basically, the more number of times the model sees your data, the better the performance gets. So right now, I'm just saying that train the model 10 number of times. So it will try and try and try and train the model 10 number of times. And the accuracy is 0.97, which is lesser than what logistic regression and that SVM. So let's take a look at model.summary as well. So right now my first hidden layer had the shape of 128 equations. Second hidden layer had the shape of 64 ReLU equations. And third hidden layer, which was the output layer really, had the shape of 10 equations of sigmoid, which is generalized sigmoid, which is nothing but softmax. And how do you calculate these parameters? I don't want to discuss at this moment, or maybe I wouldn't. But let's say if the time allows, if the mathematics allows, we will discuss how the parameters are calculated basically. But really, it's not required for you to understand what this param is doing, at least at the beginner stages. Then I'm saying some predictions over there. So this image is fed and it's getting predicted as 7, which is like totally fine. And what else? I'm printing a confusion matrix. So take a look. This confusion matrix, you can read it as 965 times it has occurred that the label was actually 0 and it was predicted as a 0. Let me zoom in a bit. I hope this thing is visible at your end. So one time it has happened that actually my digit was 0, but it was predicted as 1. You see how to read the confusion matrix. Let's take one more example. 18 times it has happened that actually it was a 7, but I predicted the 7 as 2. So that's how you read the confusion matrix. And the point being, this is the notebook structure, but what we will be doing is we will be following not the notebook structure, but the script first approach, because in the script first based approach, we can automate the things. So initially are all the import statements. There is this matplotlib.use. I don't know why I'm writing this. Not at this stage, I don't know. But if I am to take a guess, in the cloud environment, you would need to use matplotlib AGG. And we are using the cloud environment of Coder, open source. So in cloud environments, I believe this line makes sense. But even if you comment it out, I don't know what else it would change. Anyway, then I'm saying OS, operating system, make directory for me, models, make directory for me, plots. If it exists, leave it. Otherwise, create it. Load the data set, normalize it, one hot labels. Right now I'm doing the one hot encoding. So if I'm doing one hot encoding, I believe in this script I'll be using not sparse. I'll be using categorical cross entropy. So and in the sequential, I'm using first of all the flatten layer, because we are not flattening out. We are not reshaping it manually. So we are using a flatten layer and the input shape is going 28 by 28. Then I'm saying use standard scaler to scale this entire thing. Have we not normalized it anyway? We have normalized it, but we could have very well used batch normalization as well. So first of all, flatten it, then standard scaler, then 256 ReLU equations, then standard scaler. This is a pattern like standard scale, hidden layer, standard scale. Batch normalization means standard scaler really. Any kind of scalar really, any kind of normalization happening. You don't really need to go into the nitty-gritty of what kind of normalization is happening. It's just that there is some normalization happening with this batch normalization thing. I believe it's standard scalar, but it could be anything else as well. I just don't want to check, because why would I? This is not a math first module. The model compilation and see its categorical cross entropy with matrix accuracy, the same model at fit, and then I'm saving the model as in this path of models mnist model.h5. Then what else? Then I'm saying model.save. Then I'm loading the model, and after loading the model I'm saying make some predictions. np.argmax basically gives where, at which index do you see the highest value. Then we are plotting some confusion matrix, and we are plt.savefig. We are saving the confusion matrix into the plots. Let's run this file. How would you run this file? Go to the terminal and make sure in the terminal you have TensorFlow environment figured out. So I will go back to my main.py and I will see like what's the command to activate the TensorFlow environment. Come back, paste that entire code, enter it, and you see the ATS changed, and now there is TF. Now I will say that list for me all the things that I have. Go into the 14-day bootcamp, change the directory, and go into the 5 deep learning module. Now Python 3 run for me the 2 script mnist.py. Now you will see the entire workflow of how a model is trained in real life. This is how the model is trained. Epoch 1, epoch 2, and so on. It's going on. We don't train the models in notebook first approach. We do it like this. Because after the model training part comes software development part, and at least software development happens on these kind of terminals or script first approaches. So 20 epochs I'm training it for. So I'm expecting the accuracy to be better than last time, because I'm training it now for 20 epochs. And you see how fast the training is going. It's because I'm running it on GPUs. Almost done we are. So save the model, load the model, and we have two folders with us. First is mnistmodel.h5, second is plots, and I have saved some plots over here. Not me. First is the accuracy plot, and you can see that as the epoch count increases, the training accuracy keeps on increasing, but the validation on the test set, the accuracy first increases, but after that it keeps on like going consistent really. So after the epoch number 6, I would say there was no point in training the model, because after that only overfitting was happening. The gap between training and test accuracy was widening now. Confusion matrix, the entire thing is right here. Loss curve is over here. Loss meaning that just like we had depicted with the accuracy curve. So after the sixth epoch, or I should say after the third or fourth epoch really, so the loss, the error was reduced, error kept getting reduced in the training set, but over at the validation set, error kept getting rather increasing. So it means we are heading into the overfitting territory. So that's it for this video, guys. Try this on your own, and do let me know if you have any questions in the comments. Do let me know. Thanks for watching. I'll see you in the next video. In the next video, we will be discussing a CIFAR 10 dataset, which is for image classification. And instead of using ANN, we will be using CNN over there. All right, cheers. Bye bye.